is Rocio Vidalis, and today I'll be presenting you my Lab 2 motion of a falling object results in Physics 2211. Here we have a table of contents to help guide you. Okay, the falling object from rest today is going to be this cute stuffed animal beluga whale. And it is a system. The surroundings are going to be gravity and drag force. So I'll create the experiment. I'll have two codes that one will have drag force, one won't, and then we'll look at all these three models, note the difference between them. One of the computational ones is going to be more accurate, and we're going to discuss that. Alright, here's some things you need to know beforehand. First is Newton's second law of motion, more specifically the velocity update formula, the gravity and drag force, which are new to us, and keep in mind that net force does not equal 0 in our experiment. Okay, so the force of gravity can be measured through negative mg j hat, where m is for mass, g is for gravity, which has a coefficient of 9.8, and j hat is the direction. For drag force, it can be measured by multiplying the proportionality constant times the absolute value of speed and the direction of velocity. To record my observational model, I use a tracker app. I had to tilt the axes to match the pattern in which the whale was falling, and I had to set the initial y value to be 1.7 meters per positive, and the frames per second are 0.03, which is going to account for a change in time. Here's a bit more on the initial conditions. The initial velocity is 0 meters per second because remember that the object is falling from rest, and our initial is going to be 1.7 meters in the positive y direction, and it takes the whale about half a second to touch the ground. You can see that there is a downward slope, and the tracker app gave me another graph that showed the x-axis, but in this case we're only looking at the position with relation to time. Using GlowScript, I have rearranged this code for the first computational model, which does not include drag force. So we're only looking at the force of gravity in this case, which is all that F net accounts for. The force of gravity is negative ball mass times gravity times j hat. Okay, so we are using these computational models to see which one can be closest to the observational one. And in this second model, we have updated our net force equation to include drag force. Remember that drag force includes the coefficient of proportionality. In our case, it's negative 0.14499 because that is the number that got us closest to the final y position of our real life scenario, which is the closest to 0 as well. As you can see in the code, we have adjusted Fnet to not only equal the force of gravity, but also sum that with the force of drag. So why do we need to account for drag force? Well, because it leads you closer to accuracy. In real life, not only do we have gravity, but we also have drag force impacting our system. And as you can see, the side-by-side helps to show that the second one is closest to reality. For some more visual appeal, here are the three graphs side by side, and it just further proves the point that the second computational graph is closest to reality. Now that we understand that, we can further our understanding with a few questions. First is there a model that predicts a terminal velocity? The answer is yes. To the side, we have the first computational model's velocity on top and the second one on the bottom. The second computational model is less steep than the first one in terms of velocity. This means that there is a deceleration in the second one due to the drag force, and means that there will be a speed that cannot be surpassed, that is terminal velocity. Then what if the object was thrown downwards? Well, it would only decelerate faster because you're throwing it downwards, but there would still be a deceleration. To conclude, gravity and drag forces cause a falling object to reach a stopping point. Velocity is constant when only gravity is present, And once we add drag force to the net force, the acceleration of an object decreases to the point of terminal velocity. I hope you have enjoyed and understood. Thank you.